Great. So yes, I'm Adrienne Dove. I'm a postdoctoral researcher at the University of Central Florida. I'm also associated with Dan Britt's CLASS Institute. So one of the sort of goals of CLASS is to understand the surfaces of bodies, especially the moon and other airless bodies in space that have very dusty surfaces. So I'm going to talk to you a little bit today about how we understand the particle charging on these surfaces, and that will play a role in the dynamics, which Josh will talk about after this. So first, just some nice images to demonstrate my point. Dust is ubiquitous on the surfaces of airless bodies, and it's also very hazardous. I won't talk too much about the hazards today, but I will touch on that point a few times. So here we can see in a couple of the images we have Itokawa, which is an asteroid that has a very sort of varied surface with these smooth, dusty areas and then bigger rubble pile areas. This image obviously is from the surface of the moon. We don't have footprints anywhere else yet. So this one is from the surface of the moon. It's a very dusty surface, and both from going there and from laboratory studies, we can understand the dust distribution on the surfaces. And then finally, we also see some images here of Eros dust ponds. So these were images that were taken of low-lying areas in craters on Eros, and you can see that there's these very smooth regions that we think that have been attributed to dust that has probably moved there due to certain surface processes. So some additional evidence we have for dust on the lunar surface, at least, comes from surveyor observations of what's been called the lunar horizon glow. So these were observations that were taken from the surveyor, just the TV camera that was sitting on the lunar surface, looking at both sunrise and sunset. And you can see in all of these images, there's a little bit of a glow just above the surface. And this, again, has been attributed to dust. So this is thought to be dust that is probably somehow lofted up above the lunar surface, and which indicates some motion. And so we want to understand how the particles get that motion, and that we think is probably due to charging. There are some additional observations from the Apollo missions that support this case. So the LEAM instrument was the Lunar Ejecta and Meteorite instrument. And so it was sitting on the surface of the moon, and it had basically detectors that looked in different directions. There was some up-looking and then side-looking detectors. And these detectors were intended to see incoming micrometeorites, so fast-moving particles that would impact on the detector, and then we would be able to understand a little bit about their charge. However, it detected some sort of slow-moving population of dust particles that was predominantly seen at sunrise, but also some at sunset. So you can see these peaks here in the image at sunrise and sunset. And this has been attributed to dust moving on the surface of the moon. Finally, there was also the SIDE instrument. So this was an ion detection instrument that looked at the charging of the plasma above the lunar surface. So it looked at the potentials that developed above the lunar surface, and it detected about a plus 10 volt surface potentials on the lunar day side. And so I'll go a bit more into that here in a moment. So I've sort of set up the case now to say that we think there are these charged particle processes happening on the lunar surface, and likely the surfaces of asteroids and other airless bodies as well. But how does this develop? How can we understand these charged particle interactions in context? So this figure has been passed around a lot. It's basically a very complex figure showing a lot of the different plasma interactions that will help us determine surface charges and the plasma densities on surfaces. So in this figure on the left is the sun. This is sort of the driver for all of these processes. And then in this case, we have the lunar surface seen here. I'm not going to go into all of the details, but basically you can see that there's a solar wind that streams in. It hits the moon. There's not an atmosphere to protect the moon from the solar wind, so it directly gets all of these processes. On the day side, you get a general net charging of the surface, and it charges positively. This is due to photoemission from the surface. So you also have the UV light shining on the day side surface of any body in space, especially here in the inner solar system where it's more intense. And you'll get positive charging due to emitting electrons from the surface. You also then get a negative charging on the night side of the lunar surface due to the solar wind and in-streaming electrons. So electrons move quickly, and they in-stream to the lunar surface and charge it negatively. You can also see then there are some other processes going on, and the sort of glow around the moon here represents the plasma sheath that's going to be above the lunar surface. You can see it's a little bit shorter on the day side, and that just has to do with the photoelectron processes, and it's more extended on the night side. There's also some indications here of a wake boundary. So that has to do with, again, the solar wind that's streaming past the moon. You can imagine like a boat going through the water, right? You always get a wake behind it. When you have the solar wind streaming past the moon, you're going to get a wake behind it that will also act to set up some interesting electric fields and potentials on the lunar surface. And then finally, I just want to point out that there's these kind of crazy arrows right at it's called the terminator, the line between the day and the night side on the lunar surface. These arrows are indicating some sort of horizontal or vertical dust transport. So we think that these areas between the day and the night side, you could get interesting and sort of more complex electric fields at the surface, and so this could contribute to dust transport. So how do we study how these particles charge and what the relevant environments are? First, I'm not sure what everybody's background is, so I wanted to sort of set up the picture of these sheaths as I was talking about on both the day side and the night side of a surface. So in a general plasma sheath, so here on the left is our general plasma sheath, you have both ions and electrons in a plasma. It's sort of a neutral plasma. You should have equal numbers of each above the surface. But due to the fact, as I mentioned, that electrons move more quickly, they will get to the surface more easily and charge it negatively. If you can imagine then that you have this distribution of charges where sometimes it's sort of net equal and sometimes you have more negative charges on the surface, this can set up an electric field where you get a differential in charge. And that creates what's called a sheath above the surface. So you'll have a sheath region and then your net neutral plasma as well. So on the bottom is just a plot of what the electron density would look like as you go up above the surface. On the other hand, if you have a photoelectron sheath or a photoelectron plasma, this is generated, as I mentioned, by photons, generally high-energy UV photons hitting the surface, and then you get electrons that are emitted from the surface. This is the photoelectric effect, and it depends on the work function of the surface and some other properties. So in this case, you have a slightly different sheath, or this region just above the surface, where it's not neutral, and you can generate electric fields just above the surface. And because, as you can imagine, this region charges negatively and this region charges positively, the directions of electric fields will be different. So if you have charged particles sitting on the surface, they will interact differently either on the day side or the night side of the lunar surface. And then just some equations to throw in here to sort of understand this and put it all together is that the balance of the forces on a charged particle, so what will net charge this particle, is going to be a balance of forces due to the photoelectron currents, the electron plasma currents, and also other secondary electron currents. And then one thing I haven't mentioned, but that's fairly important for this case as well, is that you can also have what's called tribocharging. So far I've talked about sort of the ambient atmosphere or the ambient plasma environment that's going to charge these particles, but you also can get charging just due to contact forces. So in a basic physics class, you'll do this demonstration of like a glass rod with fur, right? And when you rub them together, it will generate a static charge on the surface. And so you can use those things. That's a demonstration of tribocharging. That's a demonstration of how, when two different materials come into contact, they'll exchange electrons and it will create a net charge on the surface. So this same thing happens with insulating grains or metallic grains on surfaces. So we need to understand, in addition to the ambient plasma processes, what happens when these grains come into contact and maybe move against each other. So one of the things in class we're interested in understanding is if you have micrometeorite bombardment or astronauts shuffling around on the surface, what's going to happen to charge up these particles and how are they going to interact with people or with instruments. So some work has been done. So I do experimental laboratory work to try to understand a lot of these processes. So some work has been done to look at how these particles charge. So a lot of times in the lab we use simulants that represent what we think make up the lunar surface or asteroid surfaces. And JSC1 is one example of that. So we've done lots of experiments to understand how they charge in plasma environments and also tribocharging. So this is just a diagram of an experimental setup in which you have some dust particles on a surface that gets shaken, and then the dust particles will interact with each other and with the surface they're on, and they'll fall into a Faraday cup. So that Faraday cup will measure the charge on the particles. So this lets us understand how they charge either when they're interacting with each other or when they're interacting in the plasma environment. So this figure then shows charge on the y-axis and the number of particles in the dropping queue. So this is just saying as you increase to the left in the plot, it's more particles have been dropped, and so they've interacted with each other more. And you can see here that you get a net sort of increase in the charge. So it's going more negative, but the charging is increasing as these particles are touching each other more. So with insulating grains, the more the things move around, they can sort of build up a charge on the surfaces of the particles. And on the right, it just shows you what sort of a surface potential on those grains would be if they were perfect spheres and other approximations. So you can see you can actually get some decent charging on these grains. We can also use these experiments to understand, as I mentioned, how these particles fit in the triboelectric series. So you can see here we have an estimate for JSC1, for JSC Mars 1, and some other just like sand particles. And this is important to understand if you have these particles, how they're going to interact with, for instance, like spacesuit material or a spacecraft, how they would charge when they come into contact with those surfaces. Finally, we can also look at how dust charges in these different sheaths. So if it's in a plasma environment or if it's in a photoelectron, in a neutral plasma environment or a photoelectron plasma environment. And we can see, so here you can see on the left is basically a UV source. And then this is distance from that UV source. So you can see here, when the dust grains are close to the UV source, they're sort of in the electron cloud that's above the source, and so they'll charge negatively. But when they're just emitting emitting electrons due to the UV themselves, they'll charge positively. And so that was what I was talking about, is how you can get these different grain charging depending on which plasma environment they're in. And so we can plot that. You can see this is just sort of a summary to show you when you have a plasma environment, you're going to get a net positive charge of the grains. And when you have a photo emission environment, when the dust grains are up in this photoelectron cloud, they're going to get negative. But triboelectric charging can sort of be a range of both. So this can really complicate the situation if you have things moving around on the surface. You can change the charges on your particles. So really quickly, we want to talk about what we can do on the lunar surface. So these are just some different ways that can be used to, or some methods that can be used to measure charges on grains in situ. So if you were to send an instrument or a spacecraft to the lunar surface, what types of instruments could you use? I mentioned LEAM earlier, and that was sort of just a charge-sensitive, sort of like a microphone. It just detected when charges hit the surface. But you can also use plasma instruments, such as it's called a Langmuir probe, which is a basic basic instrument used to measure plasma. Faraday cups, as I mentioned, and then also there's the LDEX instrument, which is currently orbiting the moon on LADEE, and that's basically a grid of wires that can detect charged particles moving through those wires. So you can imagine if you have a particle that goes through a grid, you can detect both its velocity, its position, and its charge. I don't know if I necessarily have any time to talk about this right now, but there are people working on some techniques for dust mitigation on surfaces. So this would be, for instance, spacecraft surfaces or spacesuit surfaces. And there's both passive and active types of mitigation. So you can either treat a surface so the dust will stick less, or you can have active ways, for instance, putting a voltage through a surface that would sort of throw the dust off the surface. So here's an example of a passive mitigation technique where you have less dust on the surface, and then an active mitigation technique where they sent a voltage through the surface, and you can see it very nicely cleaned it off. And this is actually Carlos Calle's work at Kennedy Space Center. And so here's my summary slide. I'll leave this up just to say that charging on particles is important. And I think I have one more slide that's the open questions you wanted to look at as well. Okay. Okay. So just some of the open questions are, what are the surface potentials on asteroids and moons as a function of local time and latitude, particularly near the terminator and poles? What are the near-surface plasma properties and electric field strengths, and how do they vary with time and latitude? What charges do dust grains acquire in the complex plasma environment, and can we find effective ways to reduce dust adhesion on spacecraft or human surfaces?
Thank you very much.